Hello, I'm Cameron Jeffries. I'm going to talk to you today about the nature of radiation, effects of radiation, radiation dose, radiation safety basics, and then radiation safety in the cardiac cath lab. Radiation is energy in the form of waves or particles. The four main types of radiation are alpha particles, beta particles, X and gamma rays, and neutrons. The physical properties of each type of radiation is determined by its relative size. Alpha particles have a large relative size and therefore have a very short range but cause a lot of ionization. They have a high potential to cause ionization. Beta particles are much smaller, about the size of an electron, and therefore have a lower level of ability to cause ionization and also a much longer range. They are best shielded by plastic. X-rays and gamma rays are essentially photons. They have a much higher level of penetration and require highly dense materials in order to be shielded, but they also spread out the ionization within a material over a lot larger area. The difference between X-rays and gamma rays is how they're produced. So X-rays are produced by artificial means using an X-ray tube, whereas gamma rays occur naturally either by decay of an atom, or we also refer to cosmic radiation as gamma rays because they come from a natural source. Otherwise, they're physically the same. X-rays and gamma rays are part of the electromagnetic spectrum. This spectrum includes radio waves, microwaves, visible light, infrared radiation, and ultraviolet radiation. X-rays and gamma rays have enough energy that they're able to cause ionization within matter. Their behavior otherwise is similar to light, except that they can't be felt or seen. Every day we're exposed to a number of natural sources of radiation. This includes cosmic radiation, cosmogenic radionuclides that are produced in the upper atmosphere by interactions of cosmic radiation, and there are also terrestrial radionuclides. These include potassium-40, uranium, and thorium. All of these nuclides have a very long half-life, which means that they're evenly spread throughout most of the Earth's crust. They make their way into foodstuffs and are also in building materials. Radiation dose is measured using three main dose quantities. We start with the absorbed dose, which is about the amount of energy deposited into a kilogram of substance by radiation. The absorbed dose must then be modified to take into account the harmful effects of different types of radiation. So alpha particles with a higher ionization potential can be more harmful. There are radiation weighting factors that are multiplied by the absorbed dose to give us the equivalent dose. This provides a comparable equivalent level of dose across all types of radiation. If we then wish to look further at the harmful effects of radiation on people, we need to weight the equivalent dose by the susceptibility to harm for different types of tissue. This is known as the effective dose. This provides a measure of risk from radiation. The units for the different radiation dose quantities are the Gray for the absorbed dose, the sievert for equivalent dose, and we also use sievert for effective dose. I mentioned that there are natural sources of radiation that we're exposed to every day. For Australia, these sources have been estimated as an average exposure per person every year. You can see from this figure that we have all of those natural sources of radiation listed with the estimated average exposure per person. So there's the cosmic radiation, there's the terrestrial radiation, which is the uranium and thorium in soil. And there's also the potassium-40 in the body and uranium and thorium in the body. The quantity of exposure every year is listed there in terms of millisievert, and these are effective doses from those radiation sources. There is also an estimated exposure for medical radiation. This is based on the average annual exposure across the entire Australian population. And it's estimated to be about 1.7 millisievert per year from medical radiation exposure. The biological effects of radiation are broken into two main areas. There are deterministic effects or immediate effects that result from an acute exposure to a high level of radiation. Examples include cataracts, skin burns, vomiting, and death. The radiation exposure impairs organ function by causing excessive amount of cell death. Deterministic effects require a threshold dose before they will be observed, and the severity is directly related to the dose. There are also stochastic effects or long-term effects. Basically, this means the chance or the risk of developing cancer. They're related to the DNA damage to a single cell, and there's no threshold, and the severity is independent of the dose. The effects do occur after a long latency period, so it's essentially the risk at some time in your lifetime that you will develop cancer. Here are some examples of deterministic effects caused during medical practice. So we have skin burns caused during fluoroscopy, radiation-induced hair loss from CT scans, and many of the early radiologists, when they first started using X-rays, lost fingers because of high levels of radiation exposure. In terms of the doses for deterministic effects, essentially the threshold for a permanent effect is about 1 gray of absorbed dose. There are some effects below 1 gray, from about 0.5 gray to 1 gray. These are temporary effects and they're not visible. Between 1 to 2 gray, there's the onset of radiation sickness. At 2 gray is the threshold for erythema, for the skin burns. This is important in the cardiac cath lab because long complex cases may result in skin burns. Death is almost certain at 10 gray of whole body exposure, but there is a good risk of death at around 4 gray of exposure if you don't have medical intervention. 100 gray to the extremities, so the fingers of the old radiologists, requires amputation because of the cellular death in the extremity. It should be noted that the first 4 lines in this graph relate to whole body exposure, so exposing the whole person to that level of radiation, which is quite different to the extremities where you're only exposing some selected tissues rather than the whole body. Stochastic effects or long-term effects are based on the probability of developing cancer. Our understanding of these effects come from a number of studies, primarily the lifespan study of atomic bomb survivors. We also have furthered our knowledge by studying Chernobyl cleanup workers, nuclear industry and nuclear shipyard workers, and our current focus in understanding stochastic effects are low dose and low dose rate radiation studies. The last point is particularly important because below about 100 millisieverts, we're not able to reliably measure the effect of radiation in terms of the lifetime probability and the lifetime risk. However, based on those studies, we do have a whole of population average risk at 5% risk of developing a fatal cancer per sievert of exposure. The risk is approximately double for children and anyone under about 19 or 20 years of age, and females have a higher risk compared to males. I've mentioned that we don't really understand, or we're not really able to measure the effect of radiation dose below about 100 millisieverts. So what we've done in terms of the risk is to apportion that at the same rate as 5% per sievert. So at 20 millisieverts, which is 0.02 sieverts, the risk of death goes to 1 in 1,000. And at 1 millisievert, the risk is estimated to be 1 in 20,000, based on that 5% risk at 1 per sievert. In comparison to other risks that we face in our daily lives, 1 millisievert per year is actually quite a low risk. You know, obviously smoking is a very high cause of death, as are accidents at home and road accidents. And I think if we're looking at 1 millisievert, we're talking about a risk of 1 in 20,000 of developing cancer that will be fatal. It should be kept in mind that the whole of population risk of cancer is about 1 in 3 to 1 in 4. So comparatively speaking, the risk of 1 millisievert per year is very low. Dose limits have been set for annual exposure to radiation that consider the risk of radiation exposure versus the benefit that's expected to accrue because of that radiation exposure. These dose limits are defined in terms of effective dose, so whole body exposure to a person, and equivalent dose to certain organs of the body. For an occupationally exposed person, someone who is working with radiation and is expected to be exposed to radiation as part of their work, their dose limit per year is 20 millisieverts in terms of effective dose. A member of the public has a lower dose limit at 1 millisievert, and we treat an embryo or fetus of a pregnant worker the same as a member of the public, so they're also subject to the 1 millisievert dose limit. The reason for the differences in these dose limits is because an occupationally exposed person has a choice to be exposed to radiation or not be exposed to radiation, whereas the public and the child do not have that choice. I've highlighted the equivalent dose limit to the lens of the eye in red. This is because that dose limit was recently reduced to 20 millisieverts per year following a discovery that there's a higher risk of exposure to the lens of the eye. I should emphasize that the organ dose limits are in terms of equivalent dose, so they haven't been modified by the type of tissue that's being exposed. They're simply absorbed dose multiplied by the radiation weighting factor. Radiation exposure is most commonly measured using a radiation badge. These are passive devices that employees and people will wear while they're working with radiation. They simply measure the amount of radiation that they're exposed to, and they're later sent away for analysis to determine the radiation exposure. It is very important that you wear your badge if you're issued with one, as we are unable to know your radiation exposure if you do not wear the badge. In the CCL, in the cardiac cath lab, typically you will wear your badge underneath a lead apron. This is because we're interested in your exposure and we're not interested in the exposure to the lead apron. I'd now like to talk about radiation protection principles. There are three main principles, starting with justification, that the benefit of the radiation exposure is going to outweigh the risk of that radiation exposure. Having satisfied ourselves that there is a benefit, we then make sure that we optimize radiation exposure. Essentially, this is based around the ALARA principle, which is as low as reasonably achievable. So rather than just stick to a fixed dose limit, we actually try to keep people's exposure as low as we can below that dose limit. Now, I've mentioned the dose limit. The third principle is limitation. So there is a hard dose limit that people must adhere to. Look, I've included a picture here to illustrate that these principles are applied in all types of workplaces. In this case, this is an example of a 1950s uranium mine in Australia. There are three radiation protection measures that you can use to protect yourself from radiation. These are time, distance, and shielding. Starting with time, it should be fairly evident that the less time you spend near a radioactive source, the lower your radiation dose will be. Therefore, it is important that you minimize the time that you spend being exposed to radiation. Distance provides protection from radiation because of the inverse square law. Radiation from a source follows the inverse square law, such that, as we see in this figure, the amount of radiation passing through a given area at 1 meter from the radiation source has to spread out as the distance is increased. So when the distance is doubled, the same amount of radiation has to travel through or pass through 4 times the amount of area. This means that the dose is reduced by 1/4 of the previous dose. Similarly, when we go out to 3 times the distance, the radiation has to go through 9 times the area, and so the dose rate at that point is 1/9. So any amount of distance that you can put between yourself and a radiation source will provide a protective factor. Shielding is our third protective measure. We can either have fixed shielding in the form of screens or lead curtains that are attached to our X-ray equipment, or we can wear protective shielding ourselves, such as lead glasses, a lead gown, or a thyroid collar. These are important protective measures to be used within the cardiac cath lab. It is preferable to use a lead apron that comes in two parts, a vest and a skirt, because of the ergonomic benefits to protect yourself from physical injury. Thyroid collars are highly effective at reducing your overall effective dose. Specifically in terms of radiation protection and radiation safety in the cardiac cath lab, there are two main roles within that lab. There is the radiographer, whose primary purpose is to supervise the use of X-rays. And the reason that they do this is to minimize exposure to the patient and to minimize exposure to the staff. The cardiologist is involved in the cardiac cath lab to provide a clinical treatment to the patient and look after the outcome for the patient. All staff are part of a team, so the radiographer and the cardiologist work together to help everyone within the process in the cardiac cath lab. In terms of staff doses in the cardiac cath lab, the main source of radiation to staff is from the patient, the scattered radiation from the patient. Therefore, it's very important to try and minimize exposure to the patient, because that will also minimize exposure to staff members. Radiation scattered from the patient is not scattered uniformly around the patient. We know that approximately 10 to 20% of X-rays emitted from the X-ray tube are scattered from the patient. About 2% of X-rays actually reach the image detector and provide the picture from the patient. Compton scatter is the predominant mechanism for radiation as it's absorbed into the patient. This means that X-ray scatters primarily back towards the X-ray tube. The result of the predominant scattering back towards the X-ray tube means that there are higher dose rates on the X-ray tube side of the patient. This is shown in an example figure here. Our preferred setup arrangement is to have the X-ray tube beneath the patient. This helps minimize exposure of staff working within the cath lab to radiation that's scattered from the patient. I will finish the lecture at this point. I've gone through basic radiation safety that will enable you to protect yourself while working within the cardiac cath lab. Thank you.